So this time we're going to look at the rational numbers Q and so last time we talked about the idea of the real numbers, which is to complete the rational numbers into something that describes the geometric notion of a line more accurately. So the ancient Greek philosophers noticed that the square root of 2, if it exists, is not a rational number. So that calls for something beyond the rational numbers. But first, to study the real numbers, we have to know what the rational numbers are. So abstractly speaking, a rational number is an element of a set, and this set has a algebraic structure. So it's what's called a group. So a group is a set with an operation that satisfies certain criteria, like it has to have an identity, and there has to be an inverse with respect to that identity for every element of the set. And also this operation, in this case it's just the addition operation, has to be what's called associative. Means that you can bracket things wherever you want. Anyway, so a group is an algebraic structure, but Q is actually more than a group. It's got two of these operations, and these operations are plus and times. And these operations work together, making it a so-called field. So it's actually Q is what's called a field. So I'm just going to be very brief in my description of this structure. What is a field? So a field is a set with two binary operations. So it has two operations. Which are in this case plus and times. And these operations satisfy a number of properties. So first of all, when you consider Q with the operation plus, it's an abelian group. Meaning that A plus B equals B plus A. And it has an identity, and the identity is what we call 0. So in this abstract language, 0 is a thing which, when added to something else, preserves that thing. So A plus 0 always equals A. It also has another structure, which is multiplication. And to be more precise, if you take all of the rational numbers except 0, and you put this operation dot or times on it, it's also an abelian group. And here the identity is 1. It's the number 1. Because 1 times anything equals anything, right? 1 times A equals A. Now, why can't 0 be a part of this group? It's because 0 doesn't have an inverse. Everything else has an inverse. Namely, the inverse of A is 1 on A. And that's only defined if A is not 0. And like we said, these two operations not only are separate operations, but they behave well with respect to each other, in the sense that multiplication distributes over addition. So if you multiply x with the sum of y and z, this is the same as adding together x times y plus x times z. So you see that the operation has distributed itself from the left-hand side to the right-hand side multiple times. And this is true for all elements f, x, y, and z inside this field Q. So that's basically a field. And these are just abstract ways of talking about properties that we all know and love. Now, Q actually has even more structure than just a field. It's what's called an ordered field. So not only is it a field, Q is an ordered field. What does this mean? This means that when we have two elements of the field, there's an order. We can compare those two elements. So here, just like before, the order is something we use all the time. It's just the less than or equal to operation, or less than or equal to relation. So let's see what this order satisfies. So this order satisfies the following properties. When you have a rational number A, of course it's equal to itself. So in particular, it's less than or equal to itself. That's kind of obvious. It's also what's called anti-symmetric, meaning that if you have A less than or equal to B, and B is less than or equal to A, then the only case when this can happen is when A is exactly equal to B. And that makes sense with numbers, right? If you have A, like 2 is less than or equal to 3, but 3 is not less than or equal to 2, and they're not equal. So the only case when both of these things can happen is when you have equality of these two numbers, or these two elements of the field. It's also what's called a transitive relation, meaning that if you have A less than or equal to B, B less than or equal to C, then that implies that A is less than or equal to C. Again, this is quite intuitive, because you just take the biggest number and it's bigger than both. And the last quality that it has is what's called a total order. So this order is total in the sense that every two elements are compatible. So for any two elements, A or B, inside of Q, you either have that A is smaller than or equal to B, or B is smaller than or equal to A. So any two numbers are comparable. So this is the abstract description of this so-called order, less than or equal to. Now, what does it mean to be an ordered field? It means that these field operations we just described above actually play well with this order. So what does that mean? So firstly, it means that the operation of addition plays well with order. So addition preserves order in the following sense. If you have two elements, A and B, we know they're comparable. So let's say that A is less than or equal to B. And now you decide to add to both sides another number C, right? So put this in a different color. This implies then, or maybe we'll use this one. This implies that A plus C is less than or equal to B plus C. So I'm going to put C here. And this is true for every A, B, and C in this set. So in this sense, if you add C, it preserves the original order you had. So we say that addition preserves order. So now what about multiplication? So multiplication is a little bit more tricky because you can multiply by positive or negative numbers. So it turns out that positive multiplication preserves positivity, in the sense that if A is bigger than or equal to 0 and B is also bigger than or equal to 0, then AB, the product, is bigger than or equal to 0. So that's true about multiplication. So these two rules describe how the order interacts with the addition and multiplication in this field. So just as an illustration of these field axioms, we're going to prove something which holds in an ordered field. So now we're thinking not just about Q, but about any ordered field that satisfies these abstract list of axioms. So let's do the following exercise. The exercise is that in any ordered field, let's call it capital F, if we have an element A, which is non-zero, so it's not equal to the additive identity of F, then we have the fact that A squared is bigger than 0. So we haven't quite introduced this notion of bigger than. Bigger than just means it's not less than or equal to. So it's the opposite of less than or equal to. Right. So here's one way to solve this exercise. So suppose that A is not equal to 0. Then either A is bigger than 0 or it's less than 0. Right? So if A is, let's say, bigger than 0, let's see what happens. So we know that A squared is certainly bigger than or equal to 0 by this axiom that positive multiplication preserves positivity. Now, we want to say that A squared is actually strictly bigger than 0 and not equal to 0. So if A is equal to 0, if A squared is equal to 0, that would mean, well, A has some kind of inverse. That means that A inverse A squared equals 0, which would mean, so the inverse cancels with one of the A's. That leaves A equals 0. But A is not 0 by assumption. So that cannot happen. So this actually implies that A squared is strictly bigger than 0. And in a similar way, if A is strictly less than 0, then minus A is strictly bigger than 0. Because you can add to both sides the negative of A. And this means that minus A squared is strictly bigger than 0. Again, by the same argument as above. So now how do we conclude then that A squared in this case is bigger than 0? Well, minus A squared by definition is minus 1 times A times minus 1 times A. That's what minus A squared is. Now, because multiplication can be, the order of operation can be swapped, it's an abelian group. This means that it's equal to minus 1 times minus 1, and then times A times A. Now, minus 1 times minus 1 is just 1, and that's A squared, which is just A squared. So therefore, A squared, which is equal to minus A squared, must be bigger than 0. Yeah, so that's an example of the kind of exercise you can do in this abstract algebra business. Anyway, so that's a little bit about Q, and next time we can discuss what it means to actually complete this algebraically very nice set of numbers into something that's geometrically also going to be very nice, and which is the beginning of the subject of real analysis.